Yes. I think I have to also extend that one because already I extended the submission of the proposal. So I think it's a quite, short time for you. So I'm going to extend that one as much as I could. So that's about the project briefing. For project briefing, I really don't want you to do anything specific. So you just start with writing up your stuff. I think I have checked like sparsely some of the proposals, and some of you already have written something. Yeah, so you can simply use it for briefing. Mainly, you just write up like we have started with the project. We do know what we need to learn, what we need to use, what we need to collect. And these are the things that we have done. So proposal and project briefing is not going to be marked like quantitatively. So it's basically based on the fact that you have done the submission. So you catch the deadline and then you have briefed what you have done. So it's not about, you don't need to be very tough with that. So just simply, we used to have progress report. But usually progress report is for a course where, like, if it was a kind of advanced course. And then you already had some deep learning knowledge, and you already had it started. Probably in such courses you don't have midterm as well. So you just have project and assignment. And then you already had it started with the project up to this point, and then you could write down something. But this is not really the case for this course. So you don't need to think about it like that. So it's just a briefing to let us know that what you are doing. But I'm going to extend it, definitely, because you just finished with the submission last week. No worries. Any other question? So shall we go on? Good. So we ended up here. So last time we ended up with the data. So we now have the last thing which I wanted to talk about in this chapter, and then we are over pretty much with everything we need to know about the fully connected neural networks. And that is the idea of Bayes normalization. So let's just start with, let's get back to some simple thing, like simple scenario, where you want to just do forward-backward pass over a feed-forward neural network, which does MNIST classification. So some of you might have noticed this when you did your assignment 1. When you trained that particular model's linear classifier perceptron, which wanted to do classification for finding X in that 3 by 3 pixel image. So that last exercise in assignment 1. And there, what you might have noticed is that depending on the sort of input you give, so if you give it 0 and 1, or if you give it 0 and 255, then you're going to see different outputs before the perceptron does the hard thresholding. Of course, this is obvious, right? But for one of them, it could be huge. For one of them, it could be in a normal range, the value, yeah? So you can extend it to the case where you do MNIST. So if you simply just implement MNIST classification, and you do it from scratch by writing down the forward and backward propagation, you're going to see that if you don't do what we're going to learn today, normalization, then starting with the image, in the hidden layers, you're going to see values which are huge, large numbers. And these large numbers, potentially, if you have a very big neural network with a kind of very messy input, these big numbers could potentially take you to the float point of your computer. Like at the point where, the computer cannot enumerate anymore. Yeah? And then you get the float error. Yeah? So that kind of problem could simply happen. And what is the idea to get rid of it? Yeah? First thing I have noticed, I have mentioned here the idea of features. So what we could say is that just sending normal input to your neural network, it's going to give you huge features. I have written here feature. And I guess you do know what I mean by feature, right? So we're going to learn more about it today when we start with convolutional neural network. But anything that you get at the output of your hidden layers, we call them feature. Because like when we do classification, we start with the image, and then we get a bunch of numbers which are going to help us do the classification at the very end of the day. And those numbers are what we call them features. I mean, you get the best idea when we start with convolutional neural network, because there you have visualization. But simply by features right now, I mean those YLs, which are the outputs of your hidden layers. Clear? Now, as I said, so you might, when you give like standard input to your neural network, you can potentially have very large features. And these features not only just take you to the float point in your forward pass, they can impact your backward pass. And then to get rid of that issue, the main idea is to just do a standardization. What does it mean? It simply means like if I have a bunch of big numbers, and if I want to do anything on them, I can just put them on the center. Like if I have a couple of numbers, say I have 3 different numbers. One of them is here, one of them is here, one of them is here, and one of them is here. One thing that I can do, I can just scale everybody and shift everybody in a form that they are relatively the same, but they are compactly centered around 0, right? So it means that I'm going to compute this distance, I compute this distance, I compute this distance, and this one. And then I am going to just, first of all, get the average distance, and then scale everybody with that average distance. Now, this guy is getting very close to the center. This guy probably comes here. This guy gets somewhere here. And this guy also gets here, right? So I scale them. And I can also shift them, right? So I can just take this guy a bit here, and this guy also a bit here, this guy also a bit here, and this guy also a bit here, right? So doing those operations on these numbers is not going to change anything, because at the end of the day in the neural network, I'm going to again multiply them with weights, add them with biases. I'm doing the same operation, right? So if instead of those weird data points, I give these new data points, my neural network at the end of the day is going to get trained. Yeah? So this is the idea which we call it a standardization. And you can do it on 2 things. You can basically do it on your input, which is the most basic thing, is input normalization. But you can also do it on your features, which is going to be the batch normalization. Okay? So just to give you a kind of rough idea on how it appears in your training. So let's just consider this simple neural networks. You have a 2-dimensional input x1, x2, and then you have 2 neurons here, 1 sigmoid, 1 neuron at the output, and probably you are going to use it for a binary classification problem, right? Now, those x1 and x2, they could be 2 different things. I mean, those 2 different numbers could be of the same nature, for example. Both of them are heights, right? Like I'm getting the height of the parents, and then I want to check whether the kid is going to be above this height or below that height. This is my classification problem, right? So x1 and x2, both of them are height, and they are in the same range, right? So 170, 180, 160, somewhere around that, correct? But they could be 2 totally different things, right? One of them could be height, the other one could be number of children, right? This is another classification problem, right? I'm getting the height and the number of children for one person, and for example, I want to just specify something, right? Some binary variable for that person. Clear? So in that case, x1, which is the height, is changing around 170, right? 180. But the other one, x2, is changing in the order of 1, 2, 3. Correct? 2 totally different scaling, because they are coming from 2 different natures. Now, how can I look at that thing? So this is, for example, one where I have both of them to be the height, and they are in the same scale. This is, for example, 2, where the things are different. And what do I mean by this chart? I simply mean like I have a data set, and I'm looking into the height of everybody in the data set. So x1 is changing in that range. So this is the top value. This is the lowest value. And everything is around, mostly within this box, but for the other one is totally different. Whereas in this case, they are just lying in the same range, correct? Now, if I wanted, for example, to use that, a simple linear classification problem, simple linear model, what do I do with that? So I'm going to give this x1 and x2 into, I'm going to multiply them with w1 and w2. Say the problem is even regression, so I don't want to do any activation, anything. I'm going to adding them up. I don't want a bias. The simplest thing you can imagine. And then this is going to be my output, right? Now, what is my output? It is simply w1 x1 plus w2 x2. And then at the end of the day, I'm going to just minimize the loss, right? It's meaning that I'm going to get this w1 x1 plus w2 x2. So this is the output. This is y, the output of my network. And then I subtract it from the true label. Yeah, say v is the true label, the true value, correct? And then I square it. And of course, I add it up over every single data point that I have in my data set. Say I have just this one particular data point, okay? Now, when I want to minimize it, I am minimizing it with respect to what? What are the variables here for training? Weights, right? So I'm minimizing over w1 and w2, right? So it's a simple quadratic problem, right? And those x1 and x2 are showing up as the coefficients of w1 and w2, correct? Now, if one of them is much more larger than the other one, what's going to happen? Exactly. So when you change w2 slightly, the whole loss is changing very slightly if x2 is very small. But if you change w1 slightly, like in example B, then loss is going to change hugely. Why? Because x1 is very large, correct? So how can I somehow show it up if I want to just think a bit more generally? So in the first example, where all the data points are in the same range, or all the entries within the data point is in the same range, my loss is going to have a kind of symmetric curvature. Yeah? So if you think of this guy as a function of w1 and w2, this is simply a quadratic function, right? And if you do those cuts on this quadratic function, you're going to get circles which are like they have the same radius pretty much in every direction, correct? But in the other case, it's going to be somehow squeezed in one direction, pressed in the other one, right? So what is going to happen? If you remember when we were talking about gradient descent, we said that this is the good guy because basically when you move, you don't really need to just tune your learning gradient for every specific direction. It's pretty much the same everywhere. But this guy is not the good one because that guy, you need to just restrict yourself with the worst dimension, worst direction, correct? So this is a sort of intuitive reason, or a bit more, say, illustrative reason why having those data points with different scaling gonna make you trouble when you are doing the backpropagation. Basically, not in the backpropagation itself necessarily, but in the convergence of your gradient descent algorithm. Okay? Now, what is the idea how we can get rid of it? So, one thing, sorry, before I just go ahead. So when we think of a more general scenario with a deep neural network, we have multiple, for example, hidden layer. The same thing that I told you about the input. So here I just consider one very dummy scenario where I have my inputs just being connected by a linear model to my output. No hidden layer, nothing. But if you have multiple hidden layers, this could happen at every single hidden layer, right? So, for example, you can start with x1 and x2 and they are in the same range, but depending on the problem that you are solving, for example, the first hidden layer, y1 and y2, could show totally different scalings, right? So it depends, again, on the problem that you have, and it could happen everywhere in the hidden layers as well. Because, for example, the first hidden layer is just grabbing one specific feature, which is very huge in dimension, in magnitude, but the other one is just taking a feature which is just changing within a very tiny range, okay? So because of that, you could have totally different scaling in the hidden layers as well. So this story that I said for this dummy example, it could happen in every single layer. And of course, when you want to just talk about the whole neural network, it's pretty much happening everywhere, right? So it's everywhere in your neural network, and it could make you trouble. So what is the main idea to resolve that issue? The main idea is that before you just pass everything to the next layer, you just do normalization, meaning that you just subtract every single point from the average, scale it by their standard deviation, and if you do that, then you have pretty much symmetric distribution around center with unit variance, and this is going to help you having like symmetric behavior in every single layer. So this is the main idea. I mean, this is not a very weird thing, but the issue is that when we want to implement it, we get into a bit of troubles, which we are going to see today. Okay? So what do I mean exactly? So say I am in layer L, or I want to just pass from layer L minus 1 to the next layer. So if I am in one particular layer, so say this is layer L minus 1, so here I have the vector y, so these are the neurons that I do have, and the outputs of these neurons specify my features, right, in that particular hidden layer. So this is going to be YL minus 1, the first entry. This is YL minus 1, the second entry, and so on till you get into your last entry, right? So whatever it is. And then the thing that you are going to do, you are going to just connect all of them to every single neuron in the next layer, right? So it's going to be connected to every single neuron in layer L. This is layer L, correct? Now, before I pass these values into the next layer, the thing that I'm going to do, I'm going to subtract every single guy from its corresponding mean. Yeah? This is what you see here. So the expectation of YL minus 1 is the average value of YL minus 1. And you might immediately ask where it comes from. I'm going to explain it. Okay? So I am going to subtract it from its mean for every single point in my data set. Every single point that I'm passing forward in this neural network, right? And then I divide it by standard deviation, which is the square root of the variance, correct? But one key point, I mean, don't get confused. Every operation here is entry-wise. Clear? So meaning that this guy is going to be subtracted from its own mean, and it gets divided by its own standard deviation, right? And this one, its own mean, its own standard deviation, and so on till the last guy. Clear? Yeah?
By own mean and own variance, we mean that, for example, we see the different samples of it?
I'm going to talk about this. Right now, assume that you know it.
Yeah,
I'm going to explain how you compute it.
So another thing which I'm thinking about, why the subscript are L minus 1?
I mean,
Why we didn't just call it L?
yeah, then everything should be L. No, I simply mean that this is the input to layer L. Say we are at layer L, so we're at this layer, and then we want to do the computation. We first get everything behind and do the standardization, and then we pass it. Okay? That's it. Okay, so any questions? So that's the main idea. Now, if you just want to have a sort of intuition or visualization of what we are doing, what we can say, say for example, we have only 2 neurons in this L minus 1 layer. Okay, so we have only 2 values for features, right? Now I can show it in 2-dimensional case, and say I, for example, pass one batch, okay, one mini batch, sorry. one mini batch over the neural network. And when I send my first mini batch, I mean, those features are somehow distributed around those points, okay? So there are multiple points, of course, within my mini batch, and everybody is there, right? But I go for my next mini batch, and I see that it's happening there, right? Third mini batch here, fourth mini batch here. I mean, if your mini batch is large enough and everything is working fine enough, it shouldn't be like this. I'm just plotting it with exaggeration. But I just want to indicate, like, you have different mini batches. You could have different distribution for specific features that you have, right? And if you do know what is the mean and what is the variance, the thing that you are going to do, you're going to get that guy, and you subtract it from its mean, so it means that you take it to the center, and then you just either squeeze it or you just scratch it in a way that it's going to get somehow unit variance. Clear? And then you're going to do it for the second mini batch, third mini batch, fourth mini batch, everybody in this architecture, right? So you don't care what is your sample anymore. Everything, you just put it at the center and scale it. Clear? Yeah.
I understand subtracting the average will move every batch into the center,
Yes.
but how come dividing the variance will make them the same size? I think it will be, if we divide by the magnitude, it will be the same, same shape, same size. But then how come dividing the variance will make them the same size?
No, you're dividing it by the square root of variance, which is the standard deviation, right?
Yeah, the standard deviation.
But you divide every single entry with its own standard deviation, right? So it means that if you have such a shape, which is like a bit larger in that direction, but here is smaller, then this guy is going to be scaled more, right? Because variance is larger, so it's going to get a smaller scaling, right? And then at the end of the day, after doing this scaling, it's going to look again like something unit variance.
So that the result batch will look like a circle.
Pretty much.
But every circle seems to be the same size. I would expect some circle be bigger, some circle be smaller. But in the image that you just showed, it seems like all batches.
No, these are before you do the scaling.
Yeah.
And after you do it, I just try, I mean, maybe it's not a good visualization, but that big one is going to be a scale the same, same size, yeah.
But we didn't divide them by the magnitude. They still become the same size.
No, you have done it by the, no, you don't think of it as a one point. Mm-hmm. This is a bunch of points, right?
It's a range of points.
Exactly. And then if you have something like variance 2, say, or a standard deviation is 2, so one random variable, then if you just sample that random variable and you just look at the axis, what's going to happen? It's going to be within that range of 2, right? This is a standard. Now if you scale it with 2, 1 over 2, then when you just again sample this scaled version, everything is going to be within the range of 1, right? It doesn't mean that every single guy is 1, of course. Yeah, but you are limiting the variance, right? So like the bell of the Gaussian distribution, I mean, you're just either, you scale it. You are either pull it or push it. Yes, but at the end of the day, it's going to be within the main bell, right? Of course, I mean, there are some particular samples happening here as well, but they are rare. Most of them are going to be within that center, right? Yeah, okay. Okay. So, any other question? Yeah.
So the variance will be different for
Different entries, you mean? Yes, of course, Yeah, this is why I indicated that variance is a vector. So everything is being done entry-wise. Yeah. Yes.
Is it needed to, at the first, we assume that we know the probability of the data and that's going to be Gaussian? And
No, you don't need that. No. I mean, it's not about Gaussian. I mean, it's any random variable, when you do that as scaling, it's going to be zero mean unit variance. It doesn't matter. No. Any other question? Okay, great. So now, yeah, so this is the idea as I told you. So you get your output of one particular layer. You do the subtraction, you do the scaling, you're going to get a zero mean unit variance features, and then you pass it to the next layer. So now, first of all, you might ask, how can I do the mean and variance? How can I compute that? And this is a kind of important question. I mean, of course, we don't have access to those values like analytically. So the thing is that we are going to approximate it from the data set. Yeah? Meaning that, for example, if I think that this guy is the input layer, the thing that I can do, I can go over all data points within my data set. I sum them up. I divide it by the number of points I have. This is going to be the approximation of the mean value. And then from that one, I can use that one to compute the variance, right? So, for example, if I have one particular input, so right now instead of YL minus 1, you think of X, which is the input. The thing that you are going to do, you're going to say that the expectation of my input is sum of all of those inputs that I have divided by their number. And if I can find those YL minus B, YL minus 1B for every single layer L, then I can do the same approximation in every single layer, right? Just a second. And then for the variance, I simply just use the definition of the variance, right? So I get every single point that I have. I subtract it from the approximation of the mean, and then I just square it, sum them up, average it, then it's going to be the expectation. It's going to be the approximation of the variance. Yes?
The approximate variance be with the b minus 1 in the denominator, because we use the approximate the empirical average, no?
From 1 to b minus 1, that is a better approximator, yes, but this is not going to really impact. I do get your point, yeah, that's going to be unbiased estimator, you're correct, yes. But you don't need to confuse yourself with that, that is a minor thing, yes?
For example, when we are running a feed forward pass and backward pass, we are using the batch to have a fewer data and something like that. But in this way, we should wait for all the batch side just for the standardization of. So
yes, that's a big, yeah.
That
is not the only problem that you have. You're going to have much bigger problems. So you are not going to worry about that one. So I'm going to explain it. Yeah, but yes, you're correct. You need to wait for all the points to pass. Exactly. So, yeah, but you got the idea how we do it, right? So this is simple. Now it's very interesting, but I'm going to show you what the troubles are. So if we think of the input layer, everything is very easy. Why? Because I would say, okay, my Y0 is simply the input, and input is something that I have inside my data set, right? So I need to just do the normalization once, yeah? Before I start to do anything, I just average everybody in this data set. I also approximate the variance or standard deviation, and then I do this normalization. It's over, right? Yeah? So this is just one-time computation. I'm going to do it before I start the training, and that's it. That's fine. So for this one, this is completely okay. But, and yeah, I'm just using this particular notation U to just indicate, wherever you see U, I basically mean the normalized version. But it's not a really big deal. I'm going to explain it everywhere that it shows up. So that thing for the input is totally fine. Because as I told you, I'm going to do just one-time computation. So meaning that I get my data set, I do compute this U function over D, which is basically this guy. And once I have done it, I just put it at the beginning of my forward pass, right? So my input from the very first layer, or the input layer, is going to be first normalized, and then it's going to pass over the whole network, right? So it's no problem with the input, everything easy, one-shot computation, that's over, right? The whole issue starts when we go for the next layers. And why this is the issue? Because if I want to do exactly the same thing as I told you here or here, if I want to do the same thing exactly as this one, I'm going to end up with a complexity pretty much like full batch training. Why? Say I am in one particular layer, so this guy is no more the input layer, it is something in between. And now I want to do the normalization here and then send it to the next layer. So what do I need to do? I need to, first of all, I need to know, for example, everybody here, the mean value and the standard deviation. Meaning that I cannot rely on one single data point. I need to pass every single data point that I have in my data set, and I just get it up to this layer L-1. I compute everybody here, so for every single data point B, so this means that this is going to be for every single data point B now, and this B should start from 1, and it's going to go to capital B, so I need to just send everybody, and wait here till everything is over. When it's over, then I am going to compute this mu1 and the standard deviation and the mean, and then of course I can do the normalization here, right? And now, when it's over, I'm going to get those normalized values. I now pass them to the next one. But again, when I want to do it, I should start again with the first data point in my data set, pass all of them, compute everything here, do the normalization, and go after, right? So meaning that for every single layer, I need to go over my whole data set. Yeah? Which is not a kind of feasible thing, right? So computationally, very high now, right? So this is one thing. But this is not the most important thing. The more important thing is that when you are computing these things, when you go forward, say I did all of that computation, I go forward completely here. When I want to get backward to my input, everybody here depends on all of the weights inside the neural network. Do you see it? Because when I got this guy, and then I normalize it by the average. But how did I compute the average? I just passed over the network up to this point, correct? So every weight behind that was involved in computation of this particular value. And now when I want to go backward, I need to take it into account for gradient computation. Yeah? So this is the most challenging part of the batch normalization. So this is not the only issue that I have. The key issue in normalization is that when you normalize any feature in the middle of your neural network, those normalized features are now depending on all of those weights. And that dependency should somehow be taken into account when you are computing the gradient. Okay? So now, what is the trick that we are going to get rid of these two issues? I mean, pretty much we're not going to get rid of any of those issues. We are just going to do it but efficiently. So the first idea is that instead of just doing the averaging over the whole data that you have, for features you are going to do it over a mini batch, which makes sense. I mean, you would say, okay, mini batch is hopefully a good estimator of my whole batch. So that is a good idea. But for the second one, you need to just do all of those back propagations that we have done before from scratch. But this time you need to take into account the batch normalization. Okay? Now, what I'm going to do now, I'm not going to expand all of things we had before with batch normalization. I'm going to do it for just one single neuron. And then you get the idea how you can do it, or you get the sense about how this normalization is going to show up in your back propagation. And once we have done it, I mean, you can hopefully extend this idea in your mind for any deep neural network. Okay? But everybody got the issues? What are the troubles now? I mean, first computation, okay, that's easy. We're just doing it over a mini batch. But the second one, did you get the idea? That everything, I mean, all those gradients that you have computed before are not valid anymore. I mean, not completely, but there are some changes here. Yeah? Okay, so let's just take a look at one single neuron. So say I have one single neuron, and this single neuron is somewhere in the middle of your neural network. Meaning that this is one particular hidden layer. Say this is the neuron. And then this guy is getting a bunch of features from the previous hidden layer. all of them are going to your neuron with some weights, and then you are doing the activation, okay? And the bias is already somehow integrated into that notation, so you don't need to think about bias anymore, okay? Now, what would be the output of this particular neuron? I'm showing it by theta because this is going to help a bit with notation. Since we have y here, I don't want to use another y here. So theta is simply the activated version of this neuron, meaning that you get your values of y, which is y1 to yn. So you have n different neurons in the previous layer. So it means that I have here y1 to yn. And then I'm going to just linearly combine them by this affine transform. So I get the linear transform, and then I pass it through the activation function. Clear? And now, the thing that is, and I assume that I have mini batches which is of size omega. Okay? Now, if I want to do just the basic forward-backward, what I'm going to do, I'm going to just start with the first point in my mini batch. I pass it, then the second point, then the third point. And every point that I pass, when it gets to that particular neuron, I'm going to compute that linear transform, and then I just activate it, right? That's it. And then when I'm doing the backward pass, I'm just coming back from my loss into the point where my neuron is. And at that particular point, I do know what is the gradient of my loss with respect to the output of that neuron. So I simply just multiply it with the activation, right? And then the next thing is that the derivative of the activation, and the next thing is that I just multiply it with the weight vector of the layer connecting these guys to my neuron, right? So this is the standard backward pass, right? And then I get to the gradient with respect to these inputs, correct? So with respect to the inputs of your neuron. Now, the thing that is now happening here with batch normalization is that, okay, we have time. So with batch normalization, what I'm going to do, I first of all need to wait. Yeah? So I start with my first point in the mini batch. I pass it. I get the first particular output, right? So, not the output of this neuron. So I need to just start from very beginning and pass every single data point inside my mini batch until I get all of the features for all of those points, right? So what I'm showing here by y omega here is then, now let's just simplify the notation here. So I am not using that L anymore, okay? I'm not using that L notation anymore. We don't have these neurons anymore, so we just focus on one neuron here. And then when I say omega, when I say omega here, what I do I mean that it's one particular point, right? So I started with one particular point x omega. I passed it through the network. It got here. I got one bunch of features, right? Then I send my next data point, then the next data point, and so on, till I am over with all of the points inside the mini batch. So omega runs from 1 to big omega, right? Now, once I have them, then I'm going to just do averaging and approximate the variance standard deviation. Once after computing that, the next thing is that I'm going to normalize, meaning that I'm going to get every single of these y omegas that I got here, subtracted from its average value, divided by its standard deviation, right? And now I'm getting something which is zero mean, unit variance, correct? Now, there is one new step here as compared to what I intuitively explained to you, and that is this kind of scaling and shifting, okay? So now, what I'm going to do next, I'm going to consider some gamma. So this guy is exactly the same vector as the size of this u, which is the size of y itself. Okay? So meaning that after doing the normalization, so after I do the normalization, these y's are going to be changed into u values, right? So these guys are going, this guy, for example, is u omega of 1. And this guy is going to be u omega of 2, and so on till u omega of n. Now, the thing is that I'm going to multiply every single guy with its corresponding gamma value, and then add its corresponding beta value. OK? Now, why we do it? I mean, why not? That's the answer. Yeah? If we can do it, why we don't do it? Yeah? So I'm not specifying these values here for you right now, because we are going to learn them. So we're giving them like weights, extra weights, and then we're going to train them. So if we can't train something, why we don't do it, right? This is the correct answer. But there is some intuition behind it as well. And then once I get this y bar, the next thing that I'm going to do is that I get this y bar, and now I pass it through my neuron, right? So I have the normalized one, and then that normalized one is going to be multiplied with the weights, and then gets activated, correct? So the thing that is now showing up here is that you don't directly connect these y guys into your final output, final neuron. You first get them, you just normalize them, then you scale them, shift them, and after doing that, now you are going to pass them to the next layer. Clear? Yeah.
So it feels like you're just adding another layer without activation.
Okay.
And then you're treating it as a new layer, and then like you're learning. And then, is this like a right interpretation?
Yeah, you can think of this batch normalization as a sort of layer, exactly. And that layer is somehow, first of all, it's somehow parameterized by this gamma and beta. This is one thing, of course. And the other thing is that it's not simply just connecting it's connected to different data points, right? All data points within the mini batch is connected to that layer. So it's not the classical layer that you think of. I'm going to draw you the computation graph. But that is a kind of right interpretation. So it's a kind of messy layer, exactly.
And do we update the gamma and beta like just?
Exactly. I'm going to show you, yeah. So, yeah.
Yeah, I was wondering, couldn't we, instead of doing this kind of computation for hidden layers or something like that, we just try to penalize some of those? For example, they're so big or so small.
Yeah, you could think of it, but then at the end of the day, it's not going to depend on the statistics of your data. You really want to reflect the statistics of your data here. And because of that, at least out of practice, it turns out that this is a more efficient way. And then how you want to regularize that, how you want to find that penalty, and what are the weights for that one. That is a hard question. It's not something easy. But this one is intuitive, and then training those gamma and beta, as you're going to see, is quite easy.
Yeah. Also, even if we use mini batch, I think there are lots of computation, and this is too time consuming.
Yeah, since you're just doing the averaging over one single mini batch, that is not going to be a huge thing. But you can think of it, as you're going to see the computation graph, you can think of it as a sort of parallel processing. Okay, so you can do it in parallel. So, of course, definitely you're increasing the computation, but that does not necessarily scale your timing linearly. So you can efficiently implement it by parallel computing. Yeah? So, definitely you are increasing the computation. Even if you try it in PyTorch, it's going to take more time to train. But it's not a huge thing. We can still handle it. And it is definitely worth it when it comes in practice, because your data, your feature could be crazy changing over dimensions. Yeah. So, OK, now, as I told you, so this is how we do the forward pass. And now, as I told you, that is scaling and shifting. These are things that we add because we're not 100% sure that this is a very good idea to shift everything to the center with unit variance. Yeah? We're not sure about that because we don't know how the weights are behaving in our neural network. So now, let me see. Yeah. So as I already mentioned, so this gamma and beta values, you can, maybe somebody tells you that I don't know. I know it from scratch. Like the naive thing is that I put beta equal, or basic thing is that I put beta to be 0, gamma to be 1 for every single entry. Then I'm going to get back exactly to that zero mean unit variance case. But in general, maybe somebody knows it by geniated information that this should be this particular thing. If that's the case, you're going to take it. You don't want to train it. But as long as you don't know it, what we do always in deep learning is that we just treat it as a bunch of parameters, and then we just update it through our training. And this is exactly what we're going to do here. So I am going to look at this gamma and beta as a bunch of extra weights, which I have in my neural network. And each time I'm updating my weights, I'm going to also update these guys. And this is going to be the thing every time, I mean, for the rest of this course and for the rest of your deep learning career. Wherever you don't know something, you just think of it as a kind of weight. Bunch of things that you are going to train it. You just let the data to find out what the right value for these guys are. Okay? Now, intuitively speaking, so we had these mini batches, and I told you that you should, I mean, by normalization, you just take it around the center, make it unit variance, but you do not necessarily know that this is a very good idea. So maybe the better idea is to just put it there with that specific scaling in every direction. Maybe, who knows, right? But if we have these degrees of freedom, this is always good to have those extra, weights in your neural network. So this is mainly the idea. So same thing as before, only I'm scaling and shifting it to one arbitrary point. Clear? So, and by that, everything is over. Now the only issue that is left is to just backpropagate to the input. Yeah? As I've written here, so in good old days, before this lecture, when we wanted to do backpropagation, everything was easy because the computation graph looked like this one, right? Why? Because every single data point is going to specify everything in the future. And then we had to only focus on the loss for that particular data point. And that data point is just going to be weighted, then give you the linear transform, and then you activate it or do whatever. And you do the rest of things till you end up with the loss, right? And then as long as you do know how to get back from your loss into z, then you just do one simple backpropagation and you get to your y, right? But now, this is getting a bit more complicated because, as I told you, you have this batch normalization thing in between. So now, let's look at it together. So what can I say? I mean, at the end of the day, when I compute my loss, my r hat is going to be 1 over omega. So this is the average over the mini batch that I have. Summation of r hat of every single of those points, right? Yeah? And this omega starts from 1, goes to omega. This is your empirical rates computed over your mini batch, correct? Now, when we were talking about no batch normalization, the point was that I wanted to compute this gradient. I simply compute the gradient of this one. And everything was somehow connected. For every single point, we were going through this exactly same path, right? But now, things are a bit different. So let's just write it down in this form. So keep this diagram in mind. So this is one particular point. I don't show any omega here. And the reason is that I don't care which point it is, right? Because for every point, everything is the same, right? But now, when I have a bunch of points inside my mini batch, it's not like that I simply pass it forward. I first compute the normalization. And that normalization is going to make the trouble. Because every single u is computed in terms of y by shifting and scaling, right? But that shift value and scale value is a function of everybody here, right? So mu and sigma, both of them are computed in terms of your data points, correct? And they are now all interconnected, right? So you cannot think of those branches being independent anymore. So first you are going to do this standardization or normalization or whatever it is. Yeah? And once you did this, now things are again back to normal. Because after that you are going to just scale and shift, which is that batch normalization idea. And once you have this guy, you are exactly back on the same point, right? Correct? So you're going to get this one, you just wait it, and then you compute this one. And after that, it's going to go pass through the whole network and give you the final loss. Clear? OK. So now, one question. So I could have a very short break, and then I keep on with this one. But I guess there are only like 8 slides left. So I can finish it and then give you a break, and then we start with CNN. Which one? So should I keep on going? So are you fine? Just finish it? OK.
No, we need rest.
OK, it's a majority vote. Should I continue? OK, it seems to be majority vote, so sorry. So now, it was my kind of democracy. Majority vote, everybody. OK. Yeah, but I'm going to be quick, so it's not a big thing. So now, if I want to do the backpropagation, as I told you, I'm not going to expand everything for you, like for the whole neural network, just for this particular neuron. So say I'm going to compute the loss, which is the output of, the risk, which is the average loss between the output of my neuron for one particular omega, and this v, which is the v of that particular point, right? The true label. And then I'm going to compute r hat in this form, and of course, I am going to, in particular, I'm going to show this r hat omega here. And by r hat omega, I simply mean, as you can see here, this guy is simply the loss between the output of my neuron for point omega and then the true label for that point. Okay? So this is the case. And of course, if I want to compute the gradient, I'm going to compute the gradient of this r hat, which means I should compute the gradient of every single r hat omega. And once I compute that, then I average all of them. Yeah? Basic thing as before. Now, getting from r hat omega to this particular point, to this one, this is quite easy. Even to this one is easy. But to this one is the standard backpropagation, right? Because I start from this guy, and then I just go backward to z. Nothing is connected here. And then from z, I'm going to go backward here. Again, nothing is connected here. So it's going to be the same for every single omega. So same computation everywhere, right? So it's up to this point is exactly what you have in the normal backpropagation. So I am going to compute the gradient with respect to z omega in terms of the gradient of the loss and the derivative of the activation function. Then I'm going to just move backward to that normalized and scaled input by simply doing the standard backpropagation over a linear layer. That's it. The whole issue starts when I want to get back to the previous layer. And this is because of those interconnections that I do have here. So up to this point, everything is fine. But then when I want to get to this point, I have a bit of trouble. So let's go together. Now, first thing, let's say I am at this point, meaning that I do know what is the gradient of this r hat with respect to y bar for every single omega that I do have here. Yeah? Now, first of all, if the next thing that I want to compute is the gradient of r hat with respect to every single u that I have here, right? So meaning that I am going to compute the, so you can think of it like this. I want to compute the derivative of my r hat. And I'm going to put this omega here because you're going to see that it's going to be important. I want to compute this one with respect to d of u, say, tau. in general, okay? For example, I want to compute the gradient of r hat with respect to u2 and u3 and so on till u omega, okay? Clear? Now, the first thing that I can look here is that, I mean, if I want to get back from y bar to u, I mean, it's just as simple as scaling and shifting, right? So because of that, I mean, you can look at every single y that you have, y bar, the scaled one that you have, as a shifted version, shifted version and a scaled version. And now if I want to compute the gradient, I can simply use the chain rule, right? And if I use the chain rule, what do you think? What's going to happen? Say I have, let me just do it like this right now. So I want to compute the derivative of r hat with respect to, I don't know, u omega, one particular omega, or u1. Look at u1, okay? If I want to do this, what is going to be if I write the chain rule? Y bar 1 times derivative of y bar 1 with respect to u1, right? I'm going to do that, right? I could have written derivative of r hat with respect to y bar 2 plus derivative of y bar 2 with respect to u1 again, right? But that one is 0, correct? Because in this figure, u1 is not going to be connected to y bar 2, right? So there is no connection from here to this one. So I could get up to this point, but if I try to get backward from y bar 2 to u1, nothing exists, correct? So this is the only thing that is left, right? And now, what is the derivative of y bar with respect to u bar? I mean, just look at this guy. Just those gamma values, correct? Great. So the derivative of y with respect to y bar with respect to u is simply that gamma. So you can simply say that whatever you have as the gradient with respect to y bar, you just entry y multiply it with that gamma, and then you're going to get the derivative with respect to the normalized version. Okay? So it is, again, a kind of simple, entry-wise computation. Now, you could get back to this point, and then the next thing is to just get back from u to y. One point here before we go backward is that at this point, I also can compute the gradient with respect to gamma and beta, correct? So for example, I could say the gradient, I mean, you can try it at home. I could say gradient with respect to gamma, just again look at, I mean, I have the gradient of r hat with respect to y bar, right? So I'm going to say what is the gradient with respect to gamma, for example. It's going to be the gradient with respect to y bar, and then y bar with respect to gamma, right? And then this guy is simply that u guy that the u value that I have. This is u1, correct? So everybody here, again, I mean, is going to be entry-wise operation. For beta, I mean, this is exactly what you did in assignment 2. So it's not going to change when you shift it. And then it's the same gradient, correct? So now, if you have that, once you do your SGD update, you can simply update your gamma and beta by some specific learning rate, right? So you have those gradients, you average them, you just compute your gradient estimator, and you update your values with that, right? OK, great. Now, the last thing. The last thing is that I want to get back from u to y, correct? Now, here, let me just focus on this r hat omega. I'm now putting this index omega. I mean, up to this point, it was not really important to have that omega because, I mean, the branches were not connected to each other. They were independent branches. But now, let's assume that I'm focusing on one particular omega, okay? That one particular omega is not only a function of y1. I mean, say the first omega is here, so it's r1. So let me just draw it like this here. So I have y1, y2 till y omega, and then these guys are going through those connections, all of these sort of connections here in between, and then you are getting u1, u2 till u omega, right? And I can say that this guy is going to be connected to R1, correct? Which is the loss, this is the loss between the output of your first branch and the label of that data point, correct? Now, I mean, you could say that it's potentially depending on U2, but all of those links are disconnected, correct? So if you compute the gradient of this R1 with respect to U2, that's going to be always 0, correct? Now I want to just compute the gradient of R hat omega with respect to any of these y values here. And this is why I'm going to show it by y tau. Because now this R1 has a gradient with respect to y1, so R omega with y omega. But R1 has also a gradient component with respect to y2. Do you agree? Yes? Because this guy also depends on y2. And so on till the last guy, right? So this is why I'm writing it down as the gradient of R hat omega for one particular omega, for example 1 here, with respect to y tau, which could be 1, 2 till big omega, correct? Now, if I want to do it, I can simply do chain rule, correct? So don't look at what I have written here. Just think of y, u, everything here to be a scalar. Then how do you write down the gradient of R1 with respect to any y tau? How do you write it down? You're going to say that this is the summation of the gradient of R1 with respect to U1 times gradient of U1 with respect to y tau, correct? Sorry. Plus gradient of R1, with respect to U2 times gradient of U2 with respect to y tau. And you keep on going by going over different values of u, right? Now, this is what I put by lambda here, right? So you compute the gradient of r hat with respect to u lambda. You do some sort of multiplication. I don't care what it is, yeah, because this is a chain rule at the end of the day. And then you multiply it by the gradient or derivative of that u lambda with respect to y tau, which is your target, correct? But now, you tell me, what is the gradient of r hat? What is the derivative of r hat 1 with respect to u2? It's going to be 0, right? Because we said this guy is not connected to u2. This is not connected to u3, not to u omega, right? It's only connected to u1, correct? So everybody here is going to be 0 after that. And this is why you can simply write it down as the gradient of r hat omega with respect to u omega, same index, times the gradient of u omega with respect to y tau. But now, the second term could have value for any omega and any tau, correct? Because u1 is not only connected to y1, it's also connected to y2 till y omega. Clear? Everybody's clear? I do know it's a bit of too much, but I mean, I just want you to get the idea. Yeah. Okay. Great. Now, if I want, first of all, one thing that, I mean, when I was doing it here on the board for you, I always think of everybody here to be a scalar. This is totally safe thing to do because every operation here is entry-wise. So this is why I'm going to just do a scalar computation here for you. And then you can just think every single entry in your vector y or in vector u going to go through exactly the same operation. Okay? Now, I have this particular u of omega in terms of every y that I have in this network. And the thing that I want to do, I want to compute the derivative of u omega, so one general omega, with respect to d of y tau. Now, the first thing that I am going to do is that I'm going to think that tau is exactly omega, meaning that I am going to compute the derivative of u1 with respect to y1. Okay? If I want to do that, what's going to show up here in this expression? Yeah? Now, let's look at it together. So this is the expression for u, right? Forget about those I values, everything. Okay? Just omega is important here. So this is the expression for u, and this is y. So u is going to be connected to the corresponding y. And also it has mu and sigma, which are also functions of y1 or y omega in general, right? So I can say that the gradient, the derivative of u omega with respect to y omega, it's going to be first 1 over sigma, or 1 over the standard deviation. Why? Because I'm looking at that expression on top. I think of mu and sigma to be constant. And if this is the case, what is the derivative of u with respect to y? Think of mu and sigma to be constant. Then your u value, u omega, is then y omega minus mu divided by sigma. So what is the derivative of u with respect to y? 1 over sigma, right? This is a constant, right? So it's divided. So you can think of it like 1 over sigma times y omega minus 1 over sigma times mu. Correct? What is the derivative now? 1 over sigma. Everybody is following? Yes? Great. So this is the derivative with respect to y when I think of this guy and this guy to be constant. Yeah? Now, next thing, I'm going to assume that this first y is a constant, sigma is a constant, but mu is a function of y. Then chain rule going to tell me that I should take the derivative of u with respect to mu, which is the first term, times the derivative of mu with respect to my y. Correct? Clear?
Can you please explain the second term again?
The second term, I mean, look at that term. This is a function of this y, this mu, and this sigma, right? And that mu and sigma, again, are functions of y, correct? Now, if I want to do chain rule, what I'm going to do? I'm going to think of mu and sigma first to be constant. I compute the partial derivative with respect to this y, yeah, which is 1 over sigma, and multiply it with the derivative with respect to y, which is 1 in that case, right? Now, next thing, I'm going to put this fixed. This is fixed. Now, mu is going to be a function of y, right? Now, again, derivative of u with respect to y in that case is going to be derivative of u with respect to mu, which is a function of y, times derivative of mu with respect to y. Correct? Everybody's following? Good. Now, last thing. I'm going to look at everything in denominator to be constant. No, the denominator, which is sigma, is going to be changing. Now, if I want to compute the derivative, chain rule tells me that this guy is the derivative of u with respect to sigma times derivative of sigma with respect to y. Correct? Yeah.
If applying chain rule, is it different component connected by the multiplication, not the plus sign? The chain rule is, we derivative the first thing times the derivative of the inside, not
Yes.
the plus.
Time and then plus everything. Like if you have a function like this. So if you have your u is a function of like say u is a function of z and I don't know r and t, and then this guy is a function of y, this guy is a function of y, this guy is a function of y. Then how you do the chain rule, you're going to write it down. The derivative of u with respect to y is going to be the partial derivative of u with respect to z times derivative of z with respect to y. Right? And then you keep on going like this. Correct? Yeah. Clear? Everybody's clear? Trust me, this is the chain rule. I mean, I do know it's too much notation here, but this is chain rule. Just get rid of all of those notation and it's going to be clear. Okay? But let's just go fast because I didn't give you a break. Yeah? So now, next thing. If I compute those derivatives, I mean, you can try it. It's quite easy. So like the derivative of u with respect to mu is simply minus 1 over sigma, right? So it's going to be minus 1 over sigma. The derivative with respect to sigma is going to be the denominator divided by denominator squared. So sigma squared minus. And then you have the whole expression. The only thing left is to compute these partial derivatives. I mean, derivative of mu and sigma. And then if you want to do that, again, this is basic computation of derivatives. So you would say my mu is a function of every y in this form. So if I want to compute the derivative of y with respect to any y here, the derivative of mu with respect to any y here, is simply 1 over omega, correct? Yeah? Okay, it's simply summation of everybody divided by omega. So every single one is, when you take the derivative, is 1 over sigma. For variance is a bit more complicated because, again, when you look at variance, it's again y here inside and mu inside. And mu itself is again a function of y, correct? And then if you do that, you need to again do the chain rule. Clear? So you're going to write it down to be the derivative simply with respect to y. And then you add it up with the derivative of this guy with respect to mu times derivative of mu with respect to y. Okay? And then if you do the computation, the good thing is that this guy is going to be 0. So even if you don't pay attention to the fact that this mu is a function of y again, you are not going to do any mistake. And you are ending up with this expression. Okay? And now you got these expressions. You just substitute them inside the original expression. So I have the derivative of sigma with respect to my y. I have the derivative of mu with respect to my y. Then the final thing that is going to happen is that I am getting this last expression I had in the previous slide and just replace them in this form. Okay? And now everything here is possible to be computed because that sigma, that mu, and those y's, all of them I have already computed. Okay? In my forward pass. Now, if I think of the case where I am computing the derivative of u with respect to one particular y, which is not exactly of the same index, so now I am looking into u omega, but I'm taking the derivative with respect to y, these two terms are going to be exactly as before. The only thing that is going to be changed is that the first term is going to be 0. Right? So here when if you look at this term here, if you want to just get the direct derivative of this guy, if you think of mu and sigma to be constant, and you want to take the derivative with respect to y tau, and that tau is not omega, what is that derivative? 0, because that is fixed in y tau, the direct derivative, right? So this is why the first term is going to be 0, but the second two terms are exactly the same thing. And then you're going to write it in that form. Okay? And then if you wrap up everything together, then you're going to end up with this expression for your gradient, which I do know it's too much computation. But I just wanted to show you that this is simply chain rule, okay? And I promise I'm going to do it less from now on. But just to give you this self-confidence that you can always backpropagate over every single network. So, anybody has a question? So as I said, I do understand if some details are not clear, but I hope that you got the main idea. You just simply, when you want to go backward, always the computation graph, and then you just consider every single branch, do the chain rule, and this is going to work. I mean, definitely, trust me. Yeah?
The normalization implemented in PyTorch?
Yes.
Oh.
Yeah, and you're going to do it in the next assignment. Yeah? So you don't really need to do that in PyTorch. I mean, some other people have done it. But then you can appreciate what they have done. Yes?
Is the sigma that you use for each layer
Sorry, I didn't get the question.
Oh, sorry. So like you do one forward pass across the whole network, and then you get the sigma for each layer. Is that how it works?
No, you compute the sigma for the whole mini batch, right?
Yeah.
Yes? So you pass the whole mini batch. So this is why I have this kind of graph here. Come on. Oh, yeah. So this is your point when you you send your first point in the mini batch, second point in the mini batch, last point in the mini batch, right? And you pass all of them. Once you have all of them, then you compute this, you compute these guys, and then in parallel you compute all of these ones. And they all together are going to contribute in your loss, correct? So for every single mini batch, you have one mu, one sigma, one vector mu, one vector sigma, of course. Yeah? But you have a bunch of different values for y. Clear? Yeah.
I don't understand why you replaced 1 over standard derivation to 0.
Which one? Here?
Yeah.
Here, this one. Because when I want to just write down the chain rule here, look, I'm taking derivative of u omega with respect to y tau, right? And I said here tau is not omega, correct? I'm looking into the case where tau. Now, if I want to compute this, if I want to use chain rule, the first thing that I do, I say, okay, mu and sigma are constant. Then I'm going to take the derivative with respect to y tau. What is the derivative? It's 0. If mu and sigma are constant, then your u omega is y omega minus mu divided by sigma, correct? These are constant, fixed numbers. Yeah? What is the derivative of this guy with respect to y tau? Here is u1. Now, what is the derivative of u1 with respect to y2? What is it?
That's 0, but we replace
Zero.
it with 1 over sigma 1.
No. Here is 0. That guy is 0.
Okay.
That guy is 0. And then the next one is that I'm now saying, okay, derivative of u1 with respect to mu, this term, times derivative of mu with respect to y2. And derivative of mu with respect to y2 is not 0 anymore. The same thing for sigma.
In case that tau is equal to omega?
That was the previous case.
Yeah.
In this case, yeah.
Separated, yeah?
Yeah, this one here is 1 over sigma then.
Yeah,
Huh?
I just thought that they are the same thing. And,
No. It's two different cases. Yeah. So, everybody's clear? Yeah? Okay. So, moral of the story, you're going to end up with such an expression, and everything is in terms of sigma, mu, which you compute in your forward pass. So now you finish your forward pass, you can do the backward pass. Okay? And my suggestion, just try to do it, at least for this single neuron, once at home. Because once you understand everything here, you're very good. You're going to have a very good understanding of backpropagation, which is the most important thing we do in deep learning. Okay? So now, just a few points here. One thing is that you might ask me that, okay, let's say we have done the training. We go forward, backward, forward. Everything is over. Now, we want to just send one new data to test this neural network. What are the values of mu and sigma? Yeah? Because we're not going to send a mini batch. We're just going to send one point, correct? Yeah? And what is the value of mu and sigma? So the trick is that we are going to collect moving average during the training. So when you train, for every single mini batch that you send, you get a mu, you get a sigma. You compute the moving average of all of them. You save it. Now when you want to test, you use those guys. Okay? And since I told you that, you can guess that when you are also doing batch normalization, the train phase and eval phase of your neural network in PyTorch is going to be different. And it's important to have .eval.train. Yes? This was also the case with dropout. So, just final things. I mean, there are some tricks if you want. I mean, if you go ahead and try to just implement it from scratch, then you need to also everything else that we had in this course, you need to have some numerical tricks to make it stable. For example, usually people add a bit of deviation here because they don't want to have sigma somewhere close to 0, which makes this scaling, going to boom up. So this is one thing. And the other thing is that you could have batch normalization. I mean, here I did it after activation, right? So when I get y, which is the activated version, then I do batch normalization. Some people do it before activation. So they get z, they do the batch normalization, then they activate. It's okay. And in practice, you usually need to try both of them, see which one works better. So there is no prescription in that sense. And the final point, as I told you, since you are doing in the inference phase, you are doing something different. I mean, you need to use those moving averages, which are not the case in training. When you are implementing in PyTorch, you should pay attention to that dot train and dot eval, which is going to be different, right? Clear? So I'm sorry. So I had been hugely over time, but we're going to have 5 minutes break, and then we start with the CNN.
Here we use the dropout. Yeah, I was wondering where we should implement it. Into our batch or
in the batch.
in the batch?
In the mini batch, yes. So you do this random.
For every single.
For every single.
missing.
Yeah,
I guess
okay.
I'll try to figure out because we're
Yeah.
short on time.
Yeah, okay. So shall we go on? I mean, I know it's just 15 minutes, but I'm not going to lose that. Okay, so just give you a brief introduction to convolutional neural networks, and then we are going to do it again on Tuesday. So now, convolutional neural networks is the most interesting part of the course probably for many of you, because this is going to start with having some bit of visualization. So the whole thing comes from this computer vision problem. So the computer vision was one of the main or very initial application people when started with artificial intelligence were looking into. And that was the kind of, algorithm which could take a look at a visualized content like images, videos, anything like that, and could just capture some or recognize some sort of pattern in it. So image classification with MNIST is one of the a simple example of that, right? Now, the idea was quite, the idea like the neural networks itself is quite old. So around 1950s, there was this Hubble and Wiesel study, which is a kind of, a bit of tough kind of study. So they, back to then it was possible. They opened up the scalp of cats and connected electrodes to the brain, and then they put in front of them some images, and they just collected some data on the electrical currents that was passing through the synapses in that brain. And then they tried to somehow understand when you show a cat something like an image which contains some particular pattern in it, how does this cat understand that pattern? They got the Nobel Prize in 1981, and the idea was somehow, or the study was somehow getting into attention mathematically in 1979 when Fukushima just proposed this neo-cognitron. So is like perceptron. Now this is the particular or individual component which is thinking of how the visualization in our brain is working mathematically. So his idea was that when we look at something, any human being, when you want to just find out one particular, you look at one image and you want to find a person in it. So you don't look at the whole image at once, but your eye is somehow going to scan it. But this is not simply that you scan every single part. You capture everything, and there are some sort of planes inside your brain which are going to just filter it over and over and over and extract features out of it. And somewhere back in your head, you're going to see the guy. And then you can focus on that one. Yeah? So it was a kind of mathematical model, which is pretty much the convolutional neural networks that we are using nowadays. Yeah? But again, back to then, there was no computation power that we could implement it. It was just a mathematical model, a computation model for visual cognition of our brain. And then LeCun came up with the idea of LeNet in 1989, which probably many of you have heard of it. So this was the first convolutional neural network, which was using basically the idea of Fukushima, but now he was doing it computationally feasible. And then he actually used backpropagation to train that architecture. Yeah? And nowadays, we have crazy CNNs with huge number of layers. So all of you watch CNN, or at least some of you, but CNN is not that CNN. So it's the friendly CNN who is convolutional neural network from now on. And this CNN is basically one feed-forward neural network, which in addition to the standard fully connected layers that we have, it also has convolutional layer and pooling layers. And these two things are used to just do feature extraction. So 3 things we need to learn. What is convolutional layer? What is pooling layer? What is feature extraction? And we are going to learn it quite soon. Okay? So you're going to learn these 3 components, and once you get it, everything is as before. You just put them next to each other, just cascade them as much as you want, and then this is going to be a CNN. Okay? Great. So now, I just wanted to give you this example, and then we're over for this week. So let's say we want to do a simple pattern recognition problem. And what is the problem here? So I want to just train one neural network, which is doing the MNIST classification, but I have one single difference to the one which we had in the previous chapter. And what is that? My image is within a very big white background. Like you got those MNIST images, and then you put it randomly on some scanner, and you scanned it. And with that one, you scan the whole background with it. Okay? Now, what I have done, what I assume that I have done, when I was preparing my data set, I was putting all of those images here on top left corner, meaning that I get those images, put it like in this very corner of my scanner, and do the scanning, right? So this is the kind of thing that I have in my data set. And now, if I want to just write or train one neural network, which does this for me with the knowledge that I have right now, I'm going to use a feed-forward, fully connected feed-forward neural network, right? Now, let's say that my images look like this one, and say that with this background, I have 3 times larger dimension, both in width and height. Okay? Meaning that before we had 28 by 28, now we have 84 by 84 pixel images. Okay? Now, instead of the thing that we had then, it's pretty much 10 times larger, so it's going to be 7,056 pixels for every single image in this new data set. Correct? And now if I want to have a feed-forward neural network, I have a much larger feed-forward input layer, right? And then I need to connect them to a hidden layer, another hidden layer, and so on until I get to the output with 10 classes. Yeah? But I can do it. So the input layer is larger, everything is as before, and then if I want to do the training on this MNIST, I need to just write down every single image in the MNIST dataset in this form, and then I just pass it through that neural network, do the gradient descent, and then I train that neural network. Okay? Now, I told you that my images, when I'm doing the training, are all in the top left corner, right? Now, I did the training, it's over. Now, after the training, if I give this new image into it, do you think that my neural network is going to recognize number 3 in it? No, probably not, right? Why?
Because it learned nothing from the white background.
Great. So the answer is correct. It might be that you come up with some crazy feed-forward neural MLP that's going to do it, but if you just go on with the standard thing that you know, most probably it's going to fail recognizing 3 in this one. And the main reason is that when you keep doing the training, your neural network is going to learn to focus only on top left part of your image, right? Only the values there are important. So the weights which are connected to them are going to get trained. Anything else is not going to get trained. Basically, it has no gradient, right? And then at the end of the day, you have a neural network. If you put an MNIST image in top left corner, it's going to recognize it. But once you just shift it somewhere else, this is going to most probably fail. Clear? Now, can we do anything about this? Given the items we had in the course up to this point, do you have any idea how I can fix that issue?
We could go through the image and identify where the number is.
No, you don't go for the smart approach, just the silly approach, based on what we have learned up to this point. Data augmentation, great. So I can do data augmentation, right? So I can get those MNIST images, and then I just shift them, put them everywhere in this background, right? And add them to my data set, and now I train my neural network with that one. Of course, this one is going to do the job, right? So if I want to do that, I need to just put these 3 everywhere in the background, anywhere possible, and then add all of them into my data set. And now that I have all of them in my data set, then this guy is going to train my neural network in a way that that one could detect 3 pretty much everywhere in this background, right? But doing that is quite huge, right? Because if I have a very big background, then I need for every single MNIST data point, I need to add lots of, augmented versions, correct? And this means like I have a huge batch. I need to go through it multiple times to get very well trained, meaning that a long training I'm going to have to train that feed-forward neural network, right? So that is not the way that our brain does it, obviously. I mean, this is what Hubel and Wiesel found out. The point was that your brain, I mean, when you know that is 3, you don't really need to also see 3 on the right down corner, right? So you just scan the whole page, and then you just try to find that pattern somewhere within the page, right? So the way that your brain does it is that it is going to break any visual, field that you have in front of you. It's going to break it into smaller fields, and then scan every single small field. And then once it finds the pattern inside that small field, it's going to say, okay, that pattern exists in this image, right? So the way that your brain is going to do it is pretty much like this. So let me just first show you. So your brain is going to just look at this image in this way, right? So it's going to say, okay, here in top corner I have 3, but if that was not here, say it was on the top right corner, so it says here it's not, here it's not, here it is, right? This is the way that your brain is going to do it. And we can actually do this by the neural network as well. How can I do it? Say I have this neural network, which I have trained to do the classification for my MNIST data set, right? And this is getting 28 by 28 image, and it's going to classify it, right? Now I'm going to just do a minor modification. So I'm going to add this class of empty, meaning that I also consider the case where there exists nothing inside that neural network. And that means that I just give a plain white page into my neural network, right? And then I can train that neural network as well, correct? So I could have this particular neural network trained. This is quite easy thing because it's going to have a much smaller input size, simply 28 by 28, 784 pixels. And then once I have trained this guy, I can scan the larger image using that guy. Meaning that I put that neural network here. I first go over the 28 by 28 pixel in the left top corner. Then if I detect it, I'm going to say yes. If no, I'm going to keep on going over every single smaller portion of my image. Correct? And then once I did it, at the very end, what I could say that for every single of them, I can just find out what is the classification. And also, if I have found any class within the MNIST, I'm going to say, okay, true, I have done this. I have found something which was within MNIST class. If no, I'm going to say false, right? I didn't find anything, right? And after I am over with the whole scanning, I am going to just OR everything at the output. If one of them is true, it means that I have found the pattern inside that. Now I'm going to just check what was the class that I have saved. I see it's class 3, so I say, okay, I found a pattern, I found a digit in this image, and that was 3. Correct? You got the idea?
But can't we like make the 3 between 2 squares? Like move it like half?
Yeah, we're going to do that, of course.
In this case, this algorithm won't work.
Yeah, it works.
But if you move like the 3 just by 1/2?
Yeah, but it doesn't matter because you're going to detect here 3, right?
I mean, if we put the 3 between the 2 windows.
Oh, yes, but I mean, you don't need to just jump that high, right? You can just slightly move your, this is what we do, right? With small stride, you just go forward, right? If you just keep it as small as possible, then you will never miss any pattern, right? So everybody's clear about this idea, what I'm doing here? So this is basically, I mean, this guy that you see is just going through this image. This is the filter inside your convolutional layer. And the whole action that you do here, you go over the first piece, then the second piece, and so on, till you are over with the whole, I mean, this whole thing that we are doing here. This is what we call it convolution. So we get a filter, that red guy, we convolve it, we just slide it over the image in a specific pattern, and then we collect all of those numbers at the output of that layer, right? This is what we call it convolution. And if you keep on doing it multiple times, then you're going to get one of those deep convolutional neural networks, which nowadays do a fantastic job in many visual computer vision stuff. So sorry for, I mean, that long pre-lecture before CNN, but I hope that everything was clear. So see you on Tuesday, and we're going to start from, I mean, here, and then we keep on going. Yeah.